Dear children, today we are going to start our last chapter of first term, that is chapter number 12 of linear programming. In this chapter, we will discuss about an optimization problem and its special case, that is linear programming. We will see what is objective function, decision variables, constraints, and how to solve graphically a linear programming problem. So, in our daily life, we came across many situations where we have to maximize or minimize a function. Such type of problems in which we have to maximize or minimize a given function under some given constraints, limitations, or you can say conditions, is called an optimization problem. And linear programming is a special type of optimization problem in which a function as well as constraints, they are linear. So let us start it with an example. Suppose a furniture dealer, it deals in only two items, tables and chairs. He has rupees 50,000 to invest and has storage space of at most 60 pieces. एक फर्नीचर डीलर है जिसके पास 50,000 रुपए हैं इन्वेस्ट करने के लिए और वो कुछ टेबल्स और चेयर्स को सेल करता है। अब उसके पास कुछ कंडीशंस हैं, लिमिटेशंस हैं कि उसके पास उन आइटम्स को स्टोर करने के लिए केवल 60 आइटम्स को वो स्टोर कर सकता है। उसके पास इतना ही स्पेस है जिसमें 60 आइटम्स स्टोर हो सकते हैं। दूसरी जो कंडीशन हमें गिवन है, दैट इज द कॉस्ट ऑफ अ टेबल इज 2500 and the cost of a chair is rupees 500. He estimates that from the sale of one table he can make a profit of rupees 250 and that from the sale of one chair a profit of rupees 75. एक टेबल से उसको 250 रुपये का प्रॉफिट होता है और एक चेयर को बेचने से उसे 75 रुपीस का प्रॉफिट होता है। He wants to know how many tables and chairs he should buy from the available money. Available money कितनी थी उसके पास? 50,000 रुपए से वो कितनी टेबल्स और चेयर्स खरीदे। ये उसकी प्रॉब्लम है कि वो कैसे ये फाइंड आउट करे कि कितने टेबल्स और चेयर्स वो खरीदे so as to maximize his total profit, जिससे कि उसे मैक्सिमम प्रॉफिट हो। दिस इज his problem. So let us take the number of chairs and the number of tables that he buys is y number of chairs and x the number of tables. Since these numbers cannot be negative, so one condition is x and y must be non-negative. He wants to maximize his profit. So we have to first form the profit function. Profit on one table is 250 and on one chair is 75. So if we denote the profit by z, then we can see that z is equal to 250x plus 75 y. This is the total profit from the sale of x tables and y chairs. His problem is he wants to maximize this profit. What are the limitations conditions with him? That he has the storage space of at most 60 pieces. So the first condition will be uh, this condition will be x plus y is less than equal to 60. Second condition is he has only 50,000 rupees to invest. So, and the cost of table is 2500. So we will have 2500 x plus, and the cost of chair is 500, and we have purchased y chairs. So the total expenditure on chairs is 500 y. It should not exceed 50,000 rupees because he has only 50,000 to invest. So this is less than equal to 50,000. You can divide it by 500 and you get this first condition, that is 5x plus y is less than equal to 100. Here we see that our profit function and the conditions we have put, all they are linear. So such type of optimization problem in which the function to be maximized or minimized as well as the limitations, constraints, all of them they are linear, it is called a linear programming problem. And the function which is to be maximized or minimized, this is called objective function. And the conditions which we have put, they are called constraints. In this, the last constraint is x and y both are non-negative. So this is called non-negative constraint. Now we will discuss some more terms related to this linear programming problem. So we can say that a linear programming problem, it is one that is concerned with finding the optimal value. Optimal value में maximum भी हो सकती है वो और minimum भी हो सकती है of a linear function, and that linear function is called objective function. जिस function की हमें maximum या minimum value find out करनी है उसे हम objective functions कहते हैं. Of several variables x and y, subject to the conditions that the variables they are non-negative and satisfy a set of linear inequalities. Last condition थी variables they are non-negative and the constraints we have taken, they are linear in the form of linear inequalities. That's what they are called, linear constraints. Why it is linear? Because all the inequalities as well as the objective function, it is a linear, so it is called a linear programming problem. Programming means it refers to the method of determining a particular program, or you can say the plan of action, how to solve it. Now, how to find the solution of such problems graphically? So, let us take the same problem here. The objective function is z equal to 250x plus 75y, and these are the constraints which we have taken. When we draw the graph of inequalities, put y is equal to 0, you will get x equal to, when y is 0 in the first equation, you will get x equal 25. So x 25 and y 0, sorry, x becomes 20, not 25 in the from the first equation. So the point is 20 comma 0. So this is the point 20 comma 0. When x is 0, y becomes 100. So 0, 100, 0, 100 is this point. You join the 2 points, you will get this line. You will get this line. And since we have slack inequality, the line will be completed. If it is slack inequality, means having only less than or greater than sign, then we will draw it by the dotted line. Now, say for the second equation, x0, y60, y0, x60. So 60, 0 and 0, 60 will be the points on the line. So one point is this 0, 60 and another is 60, 0. Join it, we will get this line. And the third is x greater than 0, y greater than 0 means our solution will be in the first quadrant. Now, for the shading of this inequality, for determining the half plane corresponding to the first equation, we will put 0, 0 here. We will get 0 less than equal to 100, which is true. It is true. So the shading of this line will be towards origin. The shading will be towards origin of the first line. For the second line, also 0, 0 satisfies because 0 is less than equal to 60. So the shading of the second line will also be towards origin. The common part of both the half planes will be this quadrilateral OABC. So this is the required common part which is satisfied by all the 4 constraints. So this common part which is determined by all the given constraints is called the feasible region. And the region other than this feasible region, that is outside this shaded part, this is called infeasible region. And the points within this feasible region is called the feasible solution. The points on the boundary of the feasible region as well as inside it, it is called the feasible solution, and the points outside it, it is called infeasible solution. Now, if it is the shaded part, or you can say the feasible region, can be enclosed within a circle, it is enclosed within can be enclosed within a circle, then it means it is a bounded region. Or you can say that, like here you can enclose it within a circle, or you can say that if this part cannot be extended indefinitely, infinitely, then it is bounded. So every point within the feasible region satisfies the given constraints, but among them, the point which gives the maximum value or minimum value of the given objective function, it is called the optimal solution. But since there are many points in the feasible region, it is not possible to check each and every point to find the maximum or minimum value. So we will have a theorem to find the point which gives us the optimal value of the solution. The first theorem is, let R is a feasible region for a linear programming problem and Z is equal to AX plus BY is the objective function. The theorem says that when Z has an optimal value, maximum or minimum, then this optimal value must occur at a corner point of the feasible region. अगर किसी ऑब्जेक्टिव फंक्शन की ऑप्टिमल वैल्यू एग्जिस्ट करती है तो वो कॉर्नर पॉइंट्स वर्टेक्स पर ही एग्जिस्ट करेगी. अब because this year we have such LPP where our feasible region is bounded, so we will discuss only the cases of bounded feasible region. And in case of bounded feasible region, we have the theorem that if R is a feasible region for a LPP and Z is equal to AX plus BY is the objective function, if R is bounded, then the objective function has both a maximum and minimum value on R. अगर हमारे पास बाउंडेड फिजिबल रीजन है तो उस रीजन का, उस प्रॉब्लम का हमारी मैक्सिमम वैल्यू भी होगी और मिनिमम वैल्यू भी एग्जिस्ट करेगी और ये वैल्यूज कॉर्नर पॉइंट पर ही एग्जिस्ट करेंगी. सो लेट अस डू सम क्वेश्चंस बेस्ड ऑन इट. The first question is solve the LPP graphically. Maximize Z is equal to 3x plus 4y. Subject to the constraints x plus y less than equal to 4. X is greater than 0 equal to 0. Y is greater than 0. These are called non-negative constraints. First we draw the inequality. तो inequality draw करने के लिए पहले corresponding equation को draw करेंगे हम. Now when y is 0, x becomes 4. So 4 comma 0 will be one point on the line, and when x is 0, y is 4, so 0 comma 4 is another point on the line. So the graph of this will be like this: 0 comma 4, 1 point, 4 comma 0 another point, join it with the complete line because we have slack inequality. And since 0 0 when you put here, 0 less than equal to 4, it will be true. So the shading, the half plane determined by this inequality will be this half plane towards the origin because origin satisfies it. And because of this, the last two constraints, our region will be only in the first quadrant because x greater than 0, y greater than 0 is in first quadrant. So this is the required feasible solution of this inequality. Now the corner points here is 4 0, 0 comma 4 and 0 0. So we will find the value of objective functions at these corner points. So at 0 0 we have 3 into 0 plus 4 into 0 0, 4 comma 0. So 3 multiplied by 4 plus 4 multiplied by 0, you will get 12. And when you put 0 4, you will get 16. Our problem is to maximize Z. So the maximum value out of this is 16. So we can say that the maximum value of Z is 16 at the point 0 comma 4. Let us take another problem of minimization. Minimize Z equal minus 3x plus 4y subject to these 4 constraints. So we will draw the graph of these inequalities first. For the first inequality, when you put x is 0, you will get y is equal to 4, and when y is 0, you will get x is equal to 8. This is for the first inequality. For the second inequality, when you put x is equal to 0, you will get y is equal to 6, and when y is 0, you will get x is equal to 4. So on the first line you have 0 4 and x 8 0. These are the 2 points on the first line, 0 4 and 8 comma 0. So this is the graph of the first inequality, 0 comma 4 and 8 comma 0. you get this line. And for the second one, you get this line. Now, in the inequality here, we have less than equal to sign in both the cases. So 0, 0 satisfies this also and this also. So the half plane determined by both the inequalities will be towards the origin. For this inequality and for the second one also, the half plane will be towards the origin. So the common part is this shaded part. And since x and y both are positive, so the shaded part will be restricted only in this first quadrant. Now we have to find the minimum value of z, so that will exist only at the corner point. So we will find the value of z at the corner points. So the corner points, they are 0, 0, 4, 0, 2, 3 and 0, 4. Here you can see that these corner points, they can easily be found from the graph, and this is also easily found. It is 2 and this is 3. If you are not able to find it from the graph, you can find this by solving the two equations 3x plus 2y equal to 12 and x plus 2y equal to 8. इन दोनों equations को solve करके आपको ये point of intersection मिल जाएगा, मीन्स ये corner point. Now, when we find the value of z at these points, 0, 0 रखा 0 आएगा, 4 0 रखेंगे यहाँ तो -12 plus 4 that is plus 0 -12 आ गया. जब आप 2 3 रखेंगे तो -3 multiplied by 2 that is -6 plus 4 multiplied by 3 that is plus 12, so it becomes plus 6, and at 0 4 the value of z is 16. So among them the least value is -12, so we can say that the minimum value of z is -12 at 4, 0. So that's all for today, students. If you have any problem, you can ask me. Thank you so much.